started. Hi everyone, and thank you for joining today's webinar on the newly released Athena Impact Estimator for Highways tool. Impact Estimator for Highways tool is a new software package based on proven lifecycle assessment models designed to allow transportation engineers and roadway designers across the country to easily measure the environmental impact of the roadway design. The base version of the tool was extensively peer-reviewed and vetted by DOT consultants, academia representatives, and I'm happy to present to you today the fully commercialized version. To download the tool for free, please visit athenasmi.org. For today are Chris Gomans, who will provide an overview of the application's functionality, methodology, and lifecycle assessment data. Finlinson, who will walk you through the program. If you have a question, please send it to me through the chat box. At the end of Grant's presentation, we'll have lots of time to answer all of your questions. And pass the microphone over to Chris and Grant.
Good afternoon, everyone. This is Chris Gomans and Grant Finlinson with the Athena Institute. Today to talk about the Impact Estimator for Highways software. We're planning to spend about 15 minutes walking through a brief overview of the Impact Estimator, an overview of the MIT Pavement Vehicle Interaction Model. Then Grant will walk us through a demonstration of using the tool. And we plan to have about 10 minutes for questions and answers. So please send your questions to Sherry via the chat utility, and she'll pose them to us during the Q&A segment. The Institute is a membership-based nonprofit organization focusing on the lifecycle assessment of the built environment. We work with edge organizations in the construction sector, doing CA for building materials and developing LCA-based tools for designers. The Institute's lead software and database developer, and I'm responsible for maintaining the Institute's web presence and its IT infrastructure. Grant is a specialist in LCA assessments using Impact Estimator software tools and is a lead researcher on a variety of LCA projects. He is additionally responsible for programming, testing, and evaluation of the Impact Estimator software tools and provides ongoing support, maintenance, calculator for building assemblies. And why do you want to apply it to roadway design? Well, North America has a significant infrastructure deficit, even after all of the recent infrastructure stimulus funding. Most of infrastructure was built during the 1950s and 70s and has subsequently used up about 97 or 79% of its service life. In an increasingly resource-constrained world due to a slower-growing economy, an aging population that translates into a smaller net tax base to draw from, and a large population drawing on fewer natural resources. The implications of that are that we need more with less, and we focus on life cycle performance. It is used by various industries when they are serious about reducing environmental footprint. We can't easily reduce our footprint if we don't know what kinds of impacts we have, how big they are, and where hot spots are. Manufacturers use LCA to reduce footprints of products. Designers use LCA to reduce footprints of their products as well, which would be buildings, highways, etc. If we don't LCA, we're just getting what sustainable is and what it isn't. LCA, we also tend to focus on a single issue or a single life phase. We may therefore be missing a major part of the equation. We may be addressing short-term improvements while incurring long-term damage. We may be fixing the wrong part of the problem. We may be shifting our environmental burdens from one phase to another. Here's a specific LCA diagram courtesy of our colleagues at MIT. At the end of life cycle stage does not come into play, as we consider roadways to be permanent pieces of infrastructure that undergo maintenance and rehabilitation into the foreseeable future. The Estimator for Highways was originally conceived of in 2009 and has been under development ever since. The beta version was released in spring 2011 and was funded by the Environment Canada and the Cement Association of Canada. Technical highway engineering expertise from Morrison Hershfeld. The commercial version was released in May 2013 and was funded by the Cement Association of Canada. The Impact Estimator for Highways, the tool could be used to model life cycle effects for roadway cross-sectional design. LCA results for product manufacturing, roadway construction, use phase, and maintenance life cycle stages. It allows custom roadway design, but also comes with a library of existing designs that can be used as a launching point for a new design, or can be duplicated and the duplicates modified. The data of library roadway designs cannot directly be altered by the end user. Rather, users can use the database library designs as starting points, as I just mentioned, by either loading and duplicating the sample project version of the library, or creating new roadway designs and choosing a library design from the scenario drop-down list. Grant will see this later during the demonstration. It allows user input use phase roadway operational energy consumption and pavement vehicle interaction action effects. Broken into two buckets: consumption due to PVI and roadway operational energy consumption. It also real-time LCA results for manufacturing, construction, maintenance, and life cycle stages. There are about 100+ roadway materials in the base, and it's growing. Of these, there are 40 component materials for which we have regionalized LCI data, and the products like asphalt or cement concretes or admixtures or a variety of custom mixed designs made up of the component materials. You create and save customized product mixes. You can make as many custom products as you want and save them in a user-defined custom product library. Material supply, transportation modes, and distances customizable. Material data can be regionalized to local transportation and energy grids. Large and equipment database is customizable to reflect the regional and seasonal working conditions and usage rates. They include above or below ground material infrastructure, such as wing, culverts, bridges, etc., and does not for site preparation or excavation, we consider to be common to comparable road types and designs. Energy and transportation data are derived from proprietary Athena databases, as well as U.S. Lifecycle Inventories database and EcoInvent database. Material presents national or industry averages for the extraction, processing, and manufacturing of materials and products. Regional grids and transportation distances are then applied to manufacturing process energies and material sourcing distances to arrive at regional data profiles. The support indicators are based on the U.S. EPA Tracy 2.0 methodology characterization factors: non-renewable fossil fuel consumption, chlorine potential, acidification potential, human particulate emissions, eutrophication potential, ozone depletion potential, and smog formation potential. Yourself, what exactly is pavement vehicle interaction anyway? The PVI is based on the latest research and model from the Concrete Sustainability Hub at the Massachusetts Institute of Technology. Image that helps to visualize the two components of PVI. Deflection causes the tires to constantly be rolling uphill. Roughness causes the tires to experience erosion along the roadway surface. PVI is a function of roadway deflection and surface roughness, both which depend on the makeup of the top layer of pavement on a given roadway surface. The model demonstrates possible increase in vehicle fuel consumption and relates effects associated with the pavement performance over time. It does this by contrasting the pavement's roughness and its deflection over time relative to a theoretical rigid and smooth roadway. They're focusing on the effect of the pavement's performance, not the life cycle vehicle effect. Fuel consumption for passenger vehicles into trucks. It models the influence of progressive increases in roughness and deflection of the roadway's top layer over time, is measured between major rehabilitations, and a calculated decline in performance as increased vehicle fuel use the pavement characteristics. The PVI inputs include the following: length, traffic speed, times or slices that represent the start and end years between major rehabilitation events, the Stand International Roughness Index values for each time segment, plastic modulus, thickness and density average values for each time segment, vehicle type, which would be passenger vehicles, annual daily traffic expected at the beginning of the project, and the projected annual growth through the end of the project lifespan. Include possible fuel consumption increase and related effects associated with the pavement performance on a per vehicle basis. Passenger vehicles and trucks, again, are based on federal registration vehicle classes. For vehicles projected to be using the roadway during the projected lifespan, the D value for projected lifespan is 50 years. The results are dependent on average vehicle fuel consumption and physical characteristics. The vehicle type characteristics, in particular the average fuel consumption, the lack of quality fuel consumption data by vehicle type at specific traffic speeds is an area of concern that is presently being looked into by our colleagues at MIT. Deficiency in the data upon which the model is dependent. Been studied in a number of one-off pavement reports. To our knowledge, it has never been incorporated into a commercial software tool. Unlike life cycle inventory data for materials, plant operation, and construction, which have been studied at length and for which there is considerable literature, P is relatively new and represents a forecast or future state scenario. A scenario carries with it a degree of uncertainty that need to be duly considered. Obviously, uncertainty would be best handled by using a statistical probability approach to the calculation model and the underlying data, something that this tool does not offer. Hence, the incentivizes those using the results from this PVI module to always acknowledge this uncertainty when discussing or presenting these results. More, we recommend that when using this module, users complete a sensitivity analysis and err on the side of reporting conservative results in any public representation of these results. Now over control to my Grant Finlayson.
Right here, we're going to switch. There, one can see the impact highways open. That's what's showing on another computer, so I think we'll go ahead. This is what the program looks like when you open it up. It's a blade at the moment. I have 2 projects already preloaded in here, but when you do open it up, these wouldn't be loaded here. These are 2 of the pre-installed, not all, but sample projects that are available in the tool at the moment. There are 4 of them, all modeled based on an Applied Research Associates report on Ontario municipal roadways. And there's, it's sort of self-described in the title here. Here we have Ontario Municipal Major Arterial, PCC or HMA road, with a 10,000 traffic number and a subgrade modulus of 50 MPa. And so that's sort of the height. They go down to 250 AADTs with 2 lanes and 30 MPa subgrade. And there ends up being 48 of them. They're pre-included when you install software. And the next iteration, there's going to be conversions added in, 96, I believe. And it's sort of setting a wide range of municipal roads that are pre-built. But to give everyone an idea of the overview of the program, I'm going to start from scratch. So I'm going to go up here and click on this icon and it's an add a project, or you can go into File and choose New. Project. this is what we have here, what we call our project level data. I'm going to get a name. Choose a location. I happen to be in Ottawa, so I'll choose Ontario East, but these are our Canadian regions that are supported. Across below the territories, I guess. This is important because that chooses the regional energy grids and transportation grids for the materials that Chris talked about earlier. Apply the Ontario electrical grid to our manufacturing processes if we Ontario, and that will affect our end results in a big way. Choose Quebec, for instance. Hydro is 9% hydro in Quebec, but in Ontario you get into natural gas and nuclear and hydro production. In Nova Scotia or Atlantic Canada you get a lot of natural gas and coal, so it great effect to results. The others we have to decide here are the project lifespan. It's defaulted at 50. You can go as low as 30 if you want, and as high as 1,000, but we defaulted at 50. The average distance to stockpile here. This is a number. We are recycling materials and removing them from the road and carting them away during a rehab step. That's the distance that we want to, that we're transferring them to disposal. So we're going to be we're calculating that transportation energy in those steps. Average distance from plant to site. This is from the concrete and asphalt plant to the site. It's put in there as an option in the idea if you wanted to model bio plants that may move along with the project or so forth if you're doing a long project. And again, it's defaulted to 30, and you can put in whatever number you want there. And we have distance of equipment depot to site, and that's the average distance that you're going to be floating your equipment from or wherever to the site itself. Down project number and project description. These are just places to make notes for yourself. So that's the basic project level data. At the top here we have some other tabs which I'm going to just quickly show you, but I'm not going to go into any details right now. Equipment. This is, as Chris said, we can customize our construction equipment energy usage. We have a transportation table here. Again, you can customize if you know where your transport materials from. The manufacturing stages, that's customizable here. I have here a roadway operating energy consumption, where you can input any number of values for these fuels if you want. For instance, if you wanted to put in the light for the road on an annual basis, you put in X number of kilowatt hours of electricity to the road, and those of burning these fuels or using these fuels will be calculated and incorporated into the results. I'll probably to construction and material transportation a little bit and maybe just show a couple of the details. For now, we've created a project, we've chosen a location, and you see here I've got a new project added in my project up here. The next thing to do is to create a roadway. So I'm just right click on down here, and a little box pops up, and you see down here we have add roadways. So we're going to add roadway, click on that. Box will pop up. So this is our design box. We can give it a name. We can call it whatever we want. I'm going to make this, let's say, an HL. We have scenarios here. You can create your own scenarios and save them, but we also have preloaded ones. And these ones that are preloaded are M48 that are available as full sample projects. You can choose one of these from this list here if you want to quickly start a project and then modify it. But I'm going to start scratch here, And then we have to fill out a bunch of these boxes. So we have initial cost. Let's say dollars. I'm going to do a 1 millimeter lane length. Make it 2 wide. I'm going to say there's pavement lift, and I'm going to say there's 1 granular layer here. For simplicity with this example, you can pretty much any you want in any number of lifts and granular layers. Choose here flexible pavement or rigid pavement. You can choose both if, for instance, you're doing a PCC, a concrete road, but you've got asphalt. You can choose both, but for this case, well, if I choose rigid, there's also an input box here for reinforcing steel. Design tool, so it's not going to calculate the amount of steel you need. You have to know that yourself and then put it in tons. For this example, we'll go with flexible pavement. And over here we have our right and left side elements, the shoulders and ditching and so forth. I'll just do one side, do the left side. I'm going to say that it has a shoulder. It also has an unpaved shoulder. I'm going to say there's 1 lift on that shoulder, and I'm going to give it a rounding of calculate some material quantities according to that. So we put in the basic information for our roadway. I'm going to click apply here. You'll see a schematic shown up here. So here we have our left side elements that we just put in. It has a paved shoulder. It has an unpaved shoulder. It has a rounding on one slope. It's not this is a schematic drawing. It's not actually drawn 4:1, but it's listed here. It calculates at 4:1. We have 2 lanes with 1 lift each, and we have a granular under the whole thing. Gives you a bit of a picture just to make sure you've not added something in you didn't want to, or that you're not missing something that you want to. And now we need to choose materials for each of these elements. And so we have 1, 2, 3, 4, 5, 6 elements there. We have 1, 2, 3, 4, 5, 6 elements down here. So if I click on, for instance, granular layer, if I click the button there, it's highlighted here, or I can click on it in the table down below. And I'm going to select a material for the granular layer. And there's a bunch of these that are in the dice. So we'll choose, let's say, granular A for that. I'm going to give width. And not quite sure what these, that's 15 meters wide with a thickness of 400 millimeters. With A, you see it gives you the density from that number in the database and the mass of that material. Again, we go down, now we have to populate the other one, so we'll go with 2 lanes. And I'm going to say that it's Hondo HMA Super Pave 12.5 FC2. This is a custom product that we designed for these sample products, and I'll show you how to do that later. A width of 5 meters wide, a thickness of 150 millimeters. Same. In 2 lift 1, I'll go and choose the same. Here that since they're both in the same lift, it's assumed the same thickness. So I can change that if I want to, if for some reason there's would be different. Of course, there's no reason they would be different. I'm going to that at 5 meters as well. The left side rounding, I'm going to choose a material, so let's go with granular B type 1 for example, a width of meters with a thickness of, well, let's go 1 feet, just consistency here, the density and mass again. There are paved shoulders and unpaved shoulders. Same thing. Here gives us an asphalt. Here's wide, let's say 150 thick, and shoulder height, and with granite B, 2 meters meters wide. And, yeah, 150. So constraints on these thicknesses, let's say, for instance, if you had these two lifts with a different thickness that says, you know, that should happen. It's due to make sure they're correct, and but it is possible to miss something there. Anyways, we've designed our roadway, basically. These are our lanes and lifts, and we could say OK here and save that. And there's an error message here to do with the PVI effects. I'm going to come back later, so I'm just going to ignore that for a second. And so, added a roadway. We called it HMA demo. I'm going to file just in case of accident, and you have to get it back again. Clicking on that, and the same thing comes up here. And you can edit this any way you want later on. The next thing to do is do a rehab schedule. Add steps to the rehab schedule. And when you click on the tab at the top here, rehab schedule, blank at the moment, and I'm going to click add, and this box will pop up. You can fill out these things again. So we're talking HMA road, so let's say after 15 years, mill and resurface rehab steps. So saying after 5 years after the initial construction, and we expect it to last 15 years, I'm going to do an asphalt partial depth reclamation, let's call it. We can put in a cost for it, $47, description, partial depth reclamation. Let's say you want to do the lanes or the shoulders, or just the lanes. I'm going to do just the lanes. I want to do tell how the road we are going to rehab. So, for instance, with the part depth reclamation, we're going to do it as part of a percentage of the surface area. And let's just say we're doing the whole thing. So it's 100% of the surface area. And when we put in 100%, we've got 10,000 square meters that we're going to reclaim, and calculated from the lane widths, kilometer road width with 2 paved lanes of 5 meters each, so that's 10,000 square meters. Here, and pick we've a number of sort of default activities, and you don't have to apply each activity to the restep. So for simplicity in the example, we're just going to say we're going to skip them all, excuse me, skip all except asphalt paving. So here, milling, asphalt pavement, I'm not skipping that, so I'm leaving that blank. I'm going to remove material here. What material I'm moving? So I'm selecting an HMA pavement, which was the Ontario SC2 12.5. I'm going to go off 40 millimeters of that, and I'm going to add that pavement back in too. So here I'm going to add a material, select HMA pavement, same pavement again, and I'm at 40 millimeters back in. First rehab step, if I click OK here, it adds here in the table. If we need to edit it, we can go over to the left-hand side, and that pops up the box there. That's how we do the step. And then you give a road for 50 years, there's a whole bunch of rehab steps, and I'm going to show you the complete files in a minute. But once you finish your rehab schedule, the next go to your PVI schedule. And this is the MIT study or model that we've incorporated into here. It requires some information from you that you knew about. This NOR PI effects. I'm going to unclick that because that was the error message I got before. It was telling that I had not completed this section. If you don't want to complete that section, you can click that button and leave it on, but we're going to do it here. So we go to the PVI section, and we're going to say with PVI need to be input for every major rehab or when you change the surface of the road. So we just put in a mill and repave rehab step at 15 years. So I'm going to say after 15 years, for the first 15 years, HMA asphalt, which let's say is the top elastic modulus of 10 PA. Thickness was, I put 150 as the top thickness, but that's probably an unrealistic number. Let's say it was 40 as a top layer, and we moved the 40 and replaced the 40. Top layer density. Now, when we choose some product like that, we can determine the density. This one happens to be 2.52 tons per meter cubed. Plastic of the, like these roads up here, we have 30, 50 PA type roads in the sample project. So let's make it a 50 for the site. And then we have the initial IRI and the final IRI index at the 0 years and the final at 15 years. And a perfect road is about 0.5, and the worst road possible is about 6. But 3 seem to be sort of typical numbers. You start off with about a 1, and when you get 3, they start thinking about having to resurface. So I'm going to use those numbers here. We have another step down here. So we've done rehab at 15 years. We need to do a new PVI section for the next period, and it would probably be another 15 years, but we've done one example here so far, so let's just say, for example, it lasts years until the 50-year lifespan. I'm using materials with the same thicknesses, so it's all the same numbers in the second row. Subgrade level, and again, when you rehab, we're restarting with an IRI of 1 and finishing with 3. So this reflection and your down here we put in our truck or vehicle usage data. For instance, these sample projects only have traffic as considered, so I'm just going to go in here with trucks, and let's say it's 10,000 daily traffic with a growth factor of 1% a year. And we've completed our PV input. And like I say, every major rehab is going to have to have a row up here for changing IRI scenarios. So we've done a PVI, we've completed our PVI, we've completed our rehab, let's say, and we've completed our design. And I click OK. And so we have our road design. And basically we're ready to look at some results. I'm going to click Save on here for that now. And then to forget this demonstration, I'm going to go up here to one of the included sample files, which is Ontario Major Arterial Road, HMA with 10,000 daily truck traffic and a submodulus of 50 MPa. I'm going to click Roadway. There here. This report, roadway design, did not have any shoulders or roundings on them. So you see here, we just have a simple 4 lanes with 2 lifts and 1 granular layer. Or 2 granular layers. And all these things are populated. The whole width is a 16-meter road. We've got 2 lanes, 2 outside lanes at 4.25, 2 inside lanes at 3.75. We've got 2 granular at 500 and 150 millimeters thick, and we've got 2 lifts of pavement at 140 and 40 millimeters thick. So it's the same thing as I just showed you, but it's elements, and I go here to rehab schedule, and there's a rehab schedule according to that A report that we talked about. So at year 8, we've got spot repairs and route and seal. At year 13, we've got spot repairs and route and seal. At year 18, we have a full depth repair with a 50 millimeter mill and surfacing. At year 23, route and seal, spot repairs, route and seal 28 years, reefs and mill at 32 years with resurface, a route and seal at 37, etc., etc. And that's sort of the complete rehab for for this road. And we've got vehicle interaction here, and PV section here, and here it is between each of those mill and repairs and resurfaces at 18 years, at 32 years, at 45 years, we have in the RI. So we're starting at 1 and ending up at 3. And we have the truck traffic down there. And that's basically what a complete road life is going to look like in a rehab schedule. Excuse me, the pieces here. 200 millimeters, same lane width, 1 granular, not 2 granular. There's not a granular A and B, just a granular lift. We've got a rehab schedule, short HM schedule, and a PI schedule. Same thing here. For instance, the difference between the top layer Los Angeles is 30 MPAs versus 10 asphalt, which we 10 as an example. And this is the IR gets switched at every resurfacing. So for instance, we've got surfacing at 25 and 30. We're not doing resurface. What we're doing here at 25 and 30 in grinding and texturization at 25, and we're set. It's taking off 5 meters each time you do that. Started off with a 200 millimeter layer. Second phase we had a 195 millimeter top layer, and then the third phase we have a 190 millimeter top layer. We have 2 road designs of the same functional road. It's a 4-lane, 1 kilometer road of the same, and we'll look at some results. So I'm going to go up here to the top bar and choose and click the reports box, and this is what shows up. We've got choose your project at the top here. So let's go to the HMA again, and the thing we look at is the bill of materials. So with rehab steps and all those and all the design questions, come up with saying that this is how much of all these materials that we're using in the figures of that roadway cycle. Our tack coats, granular A, granular B, are different super paves and asphalt sealants. If we look at the PCC bill of materials, similar thing, granular, our concrete, our reinforced steel, and our crack sealant. Then what is our life cycle effects? So that's what we call summary measures in here. So I'm clicking summary measures and table here and click show reports. Page. It's a little bit small, but we're going to leave it here. So what we have here on the left-hand side are Tracy characterization 2.0 results from the characterization factors. Our fossil fuel consumption, the global warming potential, acidification, particulate matter, eutrophication, ozone, and smog potential. And they are divided into different life cycle stages. We have the manufacturing stage, the construction phase, the maintenance stage, and use phase over here. These embodied totals are just sums of these previous columns to the left, and you see the division in the table here. And we have our use phase over here, which is our annual operating energy, our total operating energy, which is the annual times the lifespan of the road. There's 0 at the moment. If you remember the very beginning, I'll go back there quickly. At the project level, we had roadway operating energy consumption here, and this is where we could put in, let's say, the electricity for lighting. But I left it at 0 for this demonstration, so that's why those numbers are 0. And then with PVI effects here, and then the total is our totals here plus our use totals here, and that gives us a total column. I'll just go on a bigger space here just to show it here. Trace all divided by different life cycle stages, so you can choose whatever results you're looking for. If you're only looking for the initial construction, you're looking at manufacturing and construction phases. You'd only be interested in these totals here, and that's why the results are separated in the phases, and in case you use something other than just the totals. The other way to look at some results. Now, any serious analysis of these roads, you're doing this with these, and I would suggest you go up here, you export the table to Excel, and do your comparisons there. But we do produce some graphs. We can produce some graphs of these results. We can compare two projects. So up here under comparison graphs in the reports box, I choose my HMA and my PCC roads here, and I can choose all of these. I'm just going to choose a couple now, fossil fuel and global warming potential, and I'm going to show these graphs. And here we have a fuel graph, and those are results divided by different life cycle stages of this is the HM road, and this is the C road. It looks like here the road, I think I ignored the PVI effects. Go back and unclick ignore PVI effects. There. Come on. There we go. So now we have PVI effect from the HMA road. We have PVI effect from code, and the same all the other. Manufacturing versus manufacturing, maintenance versus maintenance, construction phase versus the construction phase in blue. That would do the same thing for global warming. And there, it's the same idea. We have a side-by-side comparison of these two projects. Now, it's not, if you want the numbers for these, it's not very accurate, but the visual idea of the relative effects of two different roads. Sorry, let's get rid of that little box there. And that's the actuals of it all. That's those are the results you're looking for, and mainly is what you're going to be looking for. You're going to be exporting it to Excel, and comparing numbers probably in Excel for if you're writing a report or something like that. A couple of minutes here. I'm just going to go back and show you a couple things that I glossed over. So I'm back at the project level data. I've double-clicked on a project in the tree, and this is the project data here where we choose our location, etc. And go up here and we hit the construction equipment tab. And we have all sorts of different pieces of equipment for here on the left, different equipment for different activities. And what we're trying to figure out is on-site construction energy use, which means fuel consumption, basically. We're almost all the time we're talking about fuel use and equipment. For instance, we've got here an asphalt compactor at the top, and in the base we have a usage of 0.0237 liters per ton of asphalt. Now, a great variety of conditions and weather conditions and soil conditions and usage factors that these numbers, and so we've chosen sort of a net number, but if your situation is different and you want to dig down into this, you can go change these things. And the easiest way is if you know what your fuel consumption is, you can just change the number here. So I can change that number to 5 if I want to. And there it is. Now we'll start using 0.05 for that piece of equipment. The other way to choose it is the number of columns to the right here. Production load factor, hours per day, minutes per hour, secondary fuel consumption. You can put numbers in there. So we'll change the calculation here. So for instance, for asphalt paver, if it's doing 1,215 tons a day, if we change that to 2,000 tons per day, 2,000 tons per day, you'll see here it starts off with a 0.0620. If I click 0 there, and clicked OK, I should have just carriage returned. I changed to 2,000 and changed from 0.6 or whatever the number was. I can't remember that number now. Anyways, that number changed. That's the idea. You can customize this equip table. Rotation is another tab at the top of this form. And if this is the translation of the raw materials to your plants, basically. So for instance, down here with bitumen, we've done Ontario, and the default distance for transporting bitumen is 300 kilometers by road, 0 kilometers by rail, and 0 kilometers by barge. Basically, the distance from Sydney to Toronto on. But you know that if you're modeling in some far off place and you know that you've got long distances to travel, or if you're doing it in Sarnia and you know that the distance is different, you can go and change the number here to whatever you want. So let's change it to 500 kilometers, for instance, and then our transportation data will change because we've just transported our bitumen for a further distance. Anyway, the point is that it's customizable to your own situation. The other thing to look at is that I want to add, so here at Modify Project, I can click OK. We've changed in there. The thing I want to look up here is Tools and Product Library. And this is an important one, and this is where you can make your own custom products. So basically, if you have a concrete mix design that you want to specify, and you go into database library, we have these things here, and for instance, we have a bunch of Portland concretes with different, at 30 MPa with different fly ash contents, and Portland lime cement, but those aren't. So for instance, if I choose one of them, here is the breakdown down here of that database product. If I change a little thing about this, or I want to start one from scratch, I can customize the product itself. So I'm going to duplicate it here. I'm going to I named it copy, but I'm going to call it demo C. Here is where I can change the density. So let's say my new one is going to have a density of 2.5 tons per cube, and let's just change this for something down here for fun. Let's say the water changes to 6, and the flush to 3.3 to make it. Enter. He's adding up here the total percentage by weight, 9.925. I think this will accept it within the 0.1 or so % difference. Click OK. It accepted it. But we be precise about it and percentages until we actually get 100% up here. But this is my demo PC, and this is my new material. So if I've created this new material, and you can add any of our materials in here by clicking Insert, and let's say I've some sort of add some concrete additive of some sort. I choose here, I'm going to add silica fume. I'm going to click OK. It's added silica fume down here, and I make this 0.05, and that should give us 100%. And that's a new demo PC. I click OK. I've in my new material, and if I want to go back to my roadway, I go back here to you have to go to the P1 because it's a concrete, so it will save as a concrete. And if I want to change this PC, that one we just created is available as a choice in any of the roadway elements. And I click OK, and now we've used a different concrete in that road. about it for the discussion, or for the demonstration. Yeah, I'm a couple minutes over time here. So we're going to open it up to, I'm going to back to Sherry. I'll keep control, I think, of the screen, Sherry, but you let me know if there are any questions on the chat line.
Okay, I don't see any questions at the moment, but if anyone has a question, please enter it into the chat box, and we have about 10 minutes for questions and answers.